we're recording, so today's Wednesday, August 18th. You guys know that there's a quiz coming up this Friday, and I'm gonna have you guys turn your first homework then too. Here's some topics I want to cover today and tomorrow. Today we'll probably get to about this part right here. And we'll also do a little bit of trick practice in preparation for that upcoming quiz Friday, which is just going to be on trig and vectors. So, got a donkey being pulled by two people. There's, do you guys see this dash line? Maybe that's like a Cartesian grid. Let's call that north-south line and then an east-west line, okay? North-south, east-west. Now, one guy's pulling straight north, but not with very much force, maybe like 10 newtons of force. Okay? And then this other guy is pulling exactly northeast. See, it's exactly on a 45-degree angle. And he's pulling about 4 times as hard. He's pulling with 42.4 newtons. The reason I picked that number, but you guys will see why. Yeah, maybe some of you guys know already. Huh? Now, see how I drew the 42 Newton vector as about 4 times as long as the 10 Newton vector? Yes, yeah. Okay. These are arrows, aren't they? Right. Those arrows represent vectors. These are force vectors. I drew it 4 times as long because it has 4 times the magnitude. Right? Make sense? Okay. Does that necessarily mean that the ropes that they're pulling with are a 4-to-1 ratio in terms of length? No, it has nothing to do with that. In fact, these guys might physically be side by side, so I don't know. So the lengths of these have everything to do with the force difference, right? The ratios of the forces. So, yep, we're up here in the helicopter, we're looking down, seeing that donkey pull. What is the net force on the donkey due to those the tensions in those ropes? If you know what you're doing, but some of you guys have almost solved this by now, but if you're totally stuck, then here's what I might do first is take this 42 Newton vector and break it into components. Say exactly how much north is he pulling, how much east exactly is he pulling. That'll get you started, right? You can say, well, I know how much east and how much north to this guy, and this other guy's only pulling north. Maybe you could start to combine components in the same direction. Yeah. If I do, you know what, maybe the buckets behind you, those color buckets, it's probably one of color pencils. I think it has sharpener in it. Anybody know yet what's the net force on that donkey? Anybody got it? Yeah, Sam. I want to check over. You got 50 newtons? Sam is a winner. Sam got 50 newtons. It is 50 newtons. All right. I'm going to take you guys through the process that Sam has down cut. So redraw this donkey. Got his little floppy donkey ears. Get a Cartesian grid going. Here's the east-west axis. Here's the north-south axis. Right. And remember, one guy's pulling with 10 newtons of force. Now that's kind of a small force, so hence I'm making a short vector, 10 newtons. Okay. The other guy's pulling with 4 times the force, so try to make it about 4 times as long. Well, a little bit more than that. 42.4 newtons at exactly a 45-degree angle northeast. Right, so 45 degrees east of north, something like that. Okay. And I told you guys probably a good thing to do would be to break this 42 Newton vector into components. Okay? Now you can either go up and over, or you can go over and up. Either way is okay. I'm going to go over and up. Now if I do that, maybe it's more helpful to know what is this angle right here. But I bet you guys all know that. What's this angle? Also 45 degrees, right? Okay. So it's
good to do that. You can shop for like some other angle and then sometimes make things a little easier. So I'm gonna break this into components. I'm gonna say 42 newtons northeast is, well, it's some amount north and some amount east. Here's my dashed components. Remember, if you're breaking a vector into components, you have to dash them, definitely on your AP exam, because AP otherwise interprets it as your like double counting vectors, like, oh, there's even more guys pulling the donkey, which is not what we're trying to say. This leg down here is equal to what times what? 42 times, okay, yeah, well, this one's the sine component, right? Well, if you're bouncing off this angle, I guess it's the same either way for this, right? This would be 42.4 newtons times sine of 45 degrees. Okay. Hello, Mr. Griffin. All right, where do you need me? 3217. All right, I'll be there. Awesome, thank you. Okay, and then no. Fixed. Then this one would have to be 42.4 newtons times cosine of 45 degrees. If I'm bouncing off this angle. Now, you guys probably, how many guys know that sine of 45 and cosine 45 is the same thing? Right? I mean, these two legs have to do the same thing, right? Yeah. So either way on this one. But what is 42.4 times cosine 45 degrees? Right, so this comes out to 29.98. That's extremely close to 30. In fact, it rounds to 30 to 3/6. So I'll call it 30 newtons. I'm going to hold on to that number. That's not the answer yet, but it's probably important. And then if I pop in sine, it is, of course, same thing. Get 30.0 newtons. I'm going to hold on to that number. It's not the answer yet, but it's important. So I've replaced the 42.4 newtons in terms of its components, but I still have the 10 Newton guy. So that's the other number that matters. So I just circled the three numbers. That's going to take us to the next step. And what is the next step? Well, I got this much east. I've got this much north and also this much north. Hey, do you think I could just add the two north ones together? Do that, right? Do you guys remember adding vectors together tip to tail? Tip to tail? Okay. Now that's a graphical process, but we could sort of do that here. What if I take this 10 Newton guy and I go slide it right up there? Okay. Wouldn't it look something like this? Plus 10.0 newtons right there, right? So I've just replaced this guy, so I just slid it right there. Right? And I made a tip to tail vector connection. Right? I could have done it the other way. I could have left the 10 Newton guy there, and I could have taken this 45 degree vector and gone, hey, would it end up exactly the same spot? You guys see that, right? Some textbooks teach the parallelogram method. I don't really do that, but I'll do it once for you guys. Okay. So I could have either done, or either way, it's going to leave the same spot. You guys see that? You guys like my sound effects? It's a sound of vector sliding and popping into place. And what that gives me is, if I go from the tail, I know I've got too much stuff drawn up here, more than I usually do, but if you go from the tail of the first guy, which is right here at the donkey color, and you go to the tip of the last guy, which however you get there, it's always going to lead you to the star. This is called the what kind of vector starts with an R? Resultant. Yeah, you guys remember the resultant? Okay. This is the net effect of what the donkey feels. Right? He feels this guy pulling this way, this guy pulling this way, and that dark black vector that I just drew, that's the resultant. That's what he feels overall. Right? You guys got that? Right. And do you guys see a big old right triangle right here? Big old right triangle? Right? That is, well, obviously 30 newtons wide, 30 newtons to the right. And how many newtons straight north? 40. You guys see 40? So if I combine these two, you just squeeze it on this paper. 40.0 newtons up. So 30 newtons exactly east, 40 newtons exactly north. 10 plus 30 is 40. You guys got that? Okay. So what magnitude of force does the donkey feel? You see, oh, and Sam got it already. What did you say it was? Yeah, it was 50 newtons. 50 newtons, right? You guys see how I got 50? You can do Pythagorean theorem, right? 30 squared plus 40 squared, then add this together, take square root. Right? But hey, how many of you guys notice this is a special right triangle? This is a 3, 4, 5 right triangle, isn't it? 30, 40, the other must be 50, 3, 4, 5, scaled up by a factor of 10. Yeah, this is 50 newtons, right? And that's, now that's the magnitude that the donkey feels, but there is one more part of the answer if you want to get it exactly right. Go back to this question. Right? What's the net force on the donkey? Magnitude, which we just got, that's 50 newtons. Also direction. Yeah, that is. It is. You're saying this angle right here is 53 degrees. That would be north of east. Maybe like north of east. This case, well, yeah, if you do bearing, that would be east to north, and that would be this angle right here. Something like that, right? And that would be, what angle is that? 37 degrees, right? So you can say 37 degrees, like east of north. When you say like of north, you're starting at north and you're going east of that. Okay? Or if you go north of east, you start of east and then you go north of that. And do you guys remember how to get the 37-degree angle and the 53-degree angle? You do a what process? Inverse tan. So let's say pick this one right here. I'll do that angle is equal to inverse tan. It looks like a 40 over 30 newtons. The newtons cancel out. That should give you 53 degrees. And that would be, in this case, again, north of east. Okay. That's it. Questions on the donkey? You guys ready for a quick algebra review? Okay. Now, you guys are AP. If you guys are pretty good at algebra, we'll do a recap if you guys are all on board. I'm gonna find a harder problem than I had last one in last class. What else I've got? This one looks pretty exciting here. Let's do this. Got a giant expression that looked like that. Okay, so I see a bunch of numbers. I see x a couple of places. What if you're supposed to solve for x? Okay, so you want to solve for that x, right? Well, I see it in 2 different places. Okay? Now, the long way that you can go about this is you could say, well, let me just guess and check. So what if you plug in 1? Let's see, 4 times 1 is 4, plus 3 is 7, times 3 is negative 21. This whole term would be negative 21. Plug in 1 here. 6 times 1 is 1. Here's 6. 6 times 1 is 6. Plus 1 is 7. Times 4 is 28. Negative 21 plus 28 is, what, positive 7, I think? And that is definitely not equal to 43, so 1 does not work. That's wrong. You could just like sit here and guess and check for a long time, but that would take a long time, a lot of paper, wouldn't it? Okay? So that's one thing you can use the process of algebra for. That word algebra, who knows where that comes from? What language is that from? Algebra. Yep. Close regionally. Not exactly. Anything that starts with AL, pretty much all comes from what language? Arabic. Yeah, Arabic. You guys know that these are like Arabic numerals, which actually they come from, I think, further east than that, but they were brought to Europe through the Arabs, right? This whole place value system. I mean, like Roman numerals, you don't really have a place value system. It's really hard to do higher level math. Right? You want a place value system to do that. These are Arabic numerals. The process algebra means a system for solving for the unknown. Right? So that's what we're trying to do here. And the way you want to do that is you want to go through a series of steps. At some point, a lot of steps are going to involve like undoing things that are there until the last steps can be x equals something. So what's a good first step to kick us off? Yep. So what did you say? Distribute. Yeah. So Isabel's saying to distribute. So maybe take this -3, and since it's being multiplied by this entire expression that has numbers added together, I'm going to apply it to both those on the inside. Same thing with the 4. The 4 applies to that and also that. Okay. So see, -3 times 4 is -12 versus x, -12x, plus -3 by 3 is -9. The plus 4 times 6, 24x, plus 4, 43. Okay. Still solving for x, which is still in 2 places. Now the next good step is to do what? Combine like terms. Yeah. So I see 5 different terms. Boink, 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 boink. 2 of them have x. 3 of them are just numbers. Yeah, let's combine like terms. So these 2 together make what? Just 12x. Right. 24x minus 12x is 12x. Right. These 2 together, -5, 43. Right. Next step. Yeah, add 5 over. Right. It's gonna say 12x is 48. And then finally do what to both sides? 5 by the coefficient 12. Good call. So it's going to give us x is equal to 4. I think that's right. That was right. Okay. A good thing to do, especially if it's a long process, is to take your answer, plug it back into the original expression, and see if it actually checks out. So, well, I'll just do this verbally, but you guys follow along. If it's 4 times 4 is 16, plus 3 is, hold on. I can add, is that 19? I'm sorry, yeah. All right, 19 times -3 is what, -57. Okay, so hold on to that, -57. Okay. 6 times 4 is 24, plus 1 is 25, times 4 is 100. What's 100 minus 57? 43, checks out, all good. Very good. Okay. Anyway, what do you do next? That's a slightly tricky one. Here it is. You know what? I'm not going to do this one with you guys because I think you guys are pretty good at this, but here's notes from last class. We did one that had a square root, okay, solving for something that was buried underneath the square root. So let's see, add 8 to both sides, check. And then here's the step. To undo square root, you just square both sides. Okay, that's how you unbury something from square root. Square root's gone, add 5 over, 5 by the coefficient, boom, boom, boom. Okay, okay. All right. What I do want to do with you guys is, what if you saw something like this? Like that. What's the answer to that? Yeah, there's no answer. Yeah, no solution. There is nothing you could ever plug into x to ever make that expression true. See, if you start going through some algebra steps, like, okay, well, maybe I'll add 4 over, and maybe at the same time I'll subtract this x over. Get this over. I'll get an expression that looks like this: 0 equals -5, right? Well, a couple of problems. One is that what I'm solving for is not even there, and then this isn't even true. 0 is definitely not -5, so this is no solution. Every once in a while, something like that might happen. One of the reasons I'm bringing up this example too is because I want to remind you guys that there's also a graphical approach to think about solving algebra. Okay. And this is a fun graph answer, or at least let's see, it's a graph. So you guys remember XY graphs like that? What if I turn this into an equation? I'm going to write this in blue ink. What if it was y equals x minus 4? Maybe that's one expression. And then I got y equals, I'll call this x minus 9. Right? Like, what if those were equations? Could you guys graph those? Right? So if you're ever super stuck on graphing, you can always make an XY table, right? So x could be 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Y could be mostly going to be negative territory on this one. -1, -2, -3. Right. Like that. Right, so if I plug in 0, 0 minus 4 is -4. So if x is 0, then y is -4, right there. If x is 1, y is -3. X is 1, y is -3. Okay. If x is 4, 4 minus 4 is 0. So if x is 4, y is 0. If x is 2, 2 minus 4 is -2. You guys see these are all going to line up on a straight line? Like, that process will never fail you, but sometimes it's kind of long and cumbersome. Probably an easier way to do is memorize y equals mx plus b, y equals mx plus b, you know that form, right? And there's an applied 1 coefficient in front of the x, right? That could be the slope, right? And then the -4 is the y-intercept. So look at that, y-intercept is -4. This has a slope, rise over run of 1 to 1. That's that ratio, 1. Okay, okay, good graph. What about this one, x minus 9? Well, it's the same slope, has a y-intercept of -9. Get that? Here, -9, boom, done. Graph. That would look like that, wouldn't it? Those two lines are what compared to each other? Parallel. This would also be 9. Right, so this is supposed to be parallel. Now, that means they're never going to cross. If they did cross, that would be the solution. The fact that they don't cross is also an indication that there's no solution. Right? And if they did cross, where they crossed, the x value and y value would be well, the answers to those. Okay? Sort of a graphical counterexample to a solution. Okay? Okay. You guys want to go one layer trickier? I wonder how many of you guys can solve this. MGH equals 1/2 mv squared. Who can solve for v? First person to get it, let me know. Who can solve for v? Now, those are all multiplied together. It's m times v times h equals 1/2 times m times v squared. Yeah, Sam. It is the square root of 2gh. Yeah, square root of 2gh. Okay. Now, it's the same algebra process, so go ahead and take a guess to it. Square root of 2gh. Oh, wait, you didn't say m. Is m in the answer? M? No, it's not. You got it exactly right. It cancels out. I mean, it'd be a good first step, right? Divide both sides by m. This is a not too uncommon thing to happen in this class, is that variables will cancel out. Anytime you see something cancel out in this class, what it means is that the magnitude of that variable doesn't matter. Doesn't matter if it's big or small, I think. Multiply both sides by 2, so times 2 times 2. So I'm getting 2gh is equal to v squared. Square root both sides, square root, and then swap both sides, get v is square root 2gh. That is the answer. Okay? Now I'll tell you what this means. I wonder if you guys can figure this out. What do you guys think that v stands for? What? Good guess. What's another? Velocity, right? Like speed, how fast? Also what direction? But yeah, something to do with how fast. What do you think h stands for? Height. It is a height, like a height change. You guys have a good guess on g? It is gravity, like a gravity field. Right? Now you can figure out how something's going, how fast something's going to be going as a function of the height of the building you drop it off of. If you know Earth's gravity field, that's exactly what this says. Right? You guys should solve that. This is a conservation of energy that leads to that point. We'll talk about this in a few months, but here's the story that goes with this. Back in 1589, when science was just first coming around as a concept, just the idea of like, we have some knowledge, or we think we have some knowledge, let's go out in the field and actually test and observe. That was kind of a novel idea. A guy named Galileo Galilei ran to the top of this building called the Leaning Tower of Pisa. That's what I saw, cricket. And he had a couple of objects, large and small, very large mass, very small mass. So I'm going to drop these at the same time. Guess which one hits the ground first? You guys saying same time? Same time? Huh? Hey, you know what? I bet this might be some kind of indication of that. Because what this strictly tells you is MGH, H refers to, of course, the height of the leaning tower. G is the gravity field, like Earth's gravity field. Go to a different planet, like the moon, see astronauts bounce around, boing, really slow, different gravity field on the moon, right? You drop both these things, large mass, small mass. Okay? What this equation tells you is how fast they'd be traveling after traversing this height. Right? What's their speeds? Right? But you guys see it's going to be the same at every single level. Right? That's exactly what this says. And also, the first step was that mass cancel out, which means that the magnitude of that mass doesn't matter. So yeah, these will side by side fall all the way down. Yeah, freaked out everybody at the time, like, ooh, maybe we should look into science experimentation. So yeah, there you go. You guys want to do some graphs? Do some graphs. So of course, there are many different kinds of graphs out there. There are a handful that will pop up in this class over and over again. So I draw these out. Uh, yeah, so when you guys are doing your labs, there's again just like a handful of classic graphs. If you know to look for them, then you'll see it pop up over and over again. All right. Now, you never know quite what variables you could maybe this might apply to. You guys just saw the example we did. There are variables flying all over the place. There's M, G, and H, and V. So I'm just going to very generic case call these X, Y axes. So I'll put X for all the horizontal axis, and I'll put Y on all the vertical axis. But X and Y could stand for anything. Maybe one's length of a pendulum, and the other is time period, or maybe one's like mass of some object, and the other's like how far is well. I don't know. Maybe one's the time axis. Okay. So you go to the lab, grab your data, come back, plot it, and it looks like, let's say it looks either like this, or it looks like this. Okay. And you draw a line of best fit. Now, should I connect dot to dot, or should I maybe say, well, maybe there's some error in my equipment, and I should just do a line of best fit that kind of sweeps through all of them? What do you guys think is a better way to do it? Yeah, probably the second thing I said. Okay. So this is basically a flat line, and this is basically a vertical line. Horizontal line, vertical line. Okay. Now, isn't what I'm saying in the first graph that I could make X lots of different numbers, and Y does not care what X is doing? Y's like, I don't care what X is doing. I'm just going to hang out whatever I'm doing. Right? And then, well, the flip of that is true for the second graph, right? Maybe Y could be lots of different things, and X is like, I don't care what Y is doing. I'm just going to do whatever I'm doing. Okay, see that? Okay. These are basically the same category graph in this class, and that's called no relationship. When I say no relationship, I mean between X and Y. So if I ever just say no relationship, that's the implication, right, between the variables on the graph. Okay. Is it, yeah, I see some of you guys online. Something I'm allowed to count your present, but you see here. So thank you for showing up online. Couldn't make it to class. Another common graph type is might go to the lab, get your data, come back, start plotting the points, and maybe they all look about like that. Actually, that would be maybe a little too perfect, but that's okay. And then do a line of best fit, looks something like this. What do you think that graph's called? Linear. Linear is great. And a lot of times, see how my linear graph happens to be going through the origin also? Okay. Most of the time that'll happen, not necessarily all the time. A lot of times it does. And if it does, a lot of times it's called direct. So I'll say linear or direct. Okay. Now, if it has a y-intercept, then it's probably better to just call it linear. Okay. And if it does have a y-intercept, sometimes you want to interpret what that means. If I take x all the way down to 0, y already has a starting value? Okay. Sometimes that'll happen. That means something physically. What does that mean physically? Well, it depends on what variables you have. Okay. Sometimes you'll see, think about how I want to space this out. Should we go down to the set down here? Okay. Sometimes you'll see dots that look like this. Okay. Now, at a glance, does that look linear? It does look kind of linear at a glance, doesn't it? Okay. I want to tell you guys, this is going to happen quite a bit in this class. Okay. See, if you did make it linear, you said, okay, well, I think it's a straight line. Would this have like a massively negative y-intercept then? It sure would. And maybe whatever experiment you're doing, maybe that doesn't make sense. You just pause and say, well, hold on. How would I interpret that? So if x goes to 0, y is going to be massively negative? And maybe that doesn't make sense. So you go back to the lab, make x a very small number, you grab another data point, and it's actually like right there. Right? Ooh. So maybe that wasn't linear. What shape do you think that's actually going to take? Parabola. It is going to be a parabola. Good call. Parabola. So call it parabolic. Okay. So this is like if you double x, y is going to quadruple, something like that. Pretty common. Okay. Or you go to the lab and you see a bunch of data that looks like this. Maybe a similar type story. It's like, okay, well, that looks linear, and then maybe you start to call it linear, but then you say, well, hold on a minute. That means if I took x to 0, that y would already have some very large starting value. And then maybe that doesn't really make sense if you think about logically. So you go back to the lab, make x very small, grab a data point, and you get this data point right here. Do you think it's like a curvy line? What's a good name for this type shape? What do you think? I forgot about that one, exponential. I'm not actually going to draw an exponential on here, although at a glance, exponential might look kind of like parabolic, but it's actually a completely different class of graph that I don't think ever shows up in here, or if it does, there might be like one or two exceptions. Parabolic is something like, for example, y equals x squared could be an example. I'm going to write exponential down here, which is not what this graph is supposed to be, but exponential would be something like y equals 2 to the power x, right? See, the variable would go to the exponent. Yeah, don't really look for that in class. I don't know if that's ever going to happen in this class, maybe once, but this will blow up a lot faster once x starts to get pretty big. But the one I was in the middle of talking about, this is like a root relationship, which is actually a subcategory of a power relationship, which is what parabolic is. So power, or a parabola is a specific kind of power relationship. If you have a power of 2, right? A root relationship could be like y equals the square root of x, for example. It could be a real basic shape. But you guys know that square root you can actually express as a power. That's a power of a what? 1/2. So you can think of it like a fraction power, like y equals x to the 1/2, right? Or I don't know, maybe it's a cube root, 1/3 power, something like that. So it's like kind of power relationship, just like fraction power. You guys could have, what if you have a situation where you go to the lab, you plug in small values of x, you get large values of y, and then the bigger and bigger you make x, y actually gets smaller and smaller. So if you get something that looks kind of like that, what type shape do you think that's going to make? What should I call that? Starts with an I. Called inverse relationships. You make x small, or y gets big. You make x big, y gets small. Okay? So they're doing the opposite thing of each other. Classic example, couple of masses, small guy, big guy, 1/2 kilogram, 1 kilogram. If I go out to the field and I kick both of these like a soccer ball, pew, pew, which one's going to go further? The little guy. Hey, I bet that experiment I just said, if I put mass on the x-axis and I put like kicking distance on the y-axis, I bet it would make a curve that's pretty close to that, right? The bigger it is, the less far it's going to go. It's a Newton's second law of motion, by the way. And actually, that was all I meant to give to you guys, but I'll throw in one more bonus graph that you guys might see a long time from now, maybe in January. I'll just sketch out the graph. Right? If you ever see something that oscillates, right, like oscillatory, right, or sinusoidal, I think I spelled that right. Oscillatory, sinusoidal, something goes back and forth. Right? Maybe think like maybe a pendulum, maybe a block on a spring, right? So that'll be a nice little short section we'll save for a few months from now. Okay. Okay. Any questions so far? You guys know right? All right, what do we got next? How much time we got? Okay, we're doing all right. Got about 12 minutes. Let's hit the steps of scientific method just to check this box, because I'm sure probably after taking so many years of science classes, hopefully this is baked into the way that you think about the world, right? I mean, back in 1589, Galileo was dropping stuff off the tower, freaking everybody out. This was like a new concept to think about, but hopefully you guys are pretty good at this by now. So let's just take a step. Scientific method. Okay. Usually starts with what's a pretty good textbook first step? A question, great option, question, problem, something to prompt you to want to figure something out, spark your curiosity. How does this work? Different textbooks have different steps slightly, but what's good second step? I'm going to throw it right here, a third. Hypothesis. Okay. A lot of times this is defined as an educated guess. You have some ideas about how it works. You think you have a pretty good idea, but something you might test out. A really well-written hypothesis, if you can express it like if then, if I change this variable this way, then this variable will respond this way. If you can quantify it, even better. Like, oh, I think maybe there's a direct relationship, or I think there's an inverse relationship, something like that. And really importantly in science, guys, do you want a hypothesis? You guys ready for a tricky question? A really well-crafted hypothesis. Is this something that is provable or falsifiable? Which one of those is the best answer? How many guys think it's better to be falsifiable than provable? Because that's the answer. That's the answer. Okay. If you're really good at scientific thinking, because the problem with creating something that's only provable is that if it's never falsifiable, then either you're always just going to get the answer you want. So what if you really learn? Okay. If you can set up something that's falsifiable and you're trying to poke holes in it, okay, I think this is how this works, but kind of poke holes in it, come in every angle I can think of, and I can never disprove it, and no one else can disprove it, then that's probably an indication that it's at least a possibility of how the universe works. What's the good stuff I missed? Yeah, like background research. Okay. So what's out there? Did anybody tackle this question? What's the literature on this? What kind of insights do people have? Okay. Maybe you're not satisfied with that, so you create your own hypothesis, experiment. It's the heart of the scientific method. You're gonna data analysis, analyze that data. So in this class, there's two main ways we're gonna do that in this class. We do graphs. Graphs going to be a big deal in this class. Equations. Graphs and equations. Right? Basically, those graphs I was just showing you guys a minute ago. Right? You make equations out of those too, right? And then some kind of conclusion. Right? You can add on to that. You can say, if you're real serious, maybe publish this in a journal and have it peer reviewed and all that stuff, right? Guys good there? All right. You guys have sufficiently learned science. I want to tell you guys about the metric system. You guys ready to learn about the metric system? So, metric system. Say we go back 500 years ago, back to the time machine. Maybe you got the time that Galileo was dropping stuff off the tower. And you want to measure things, write it up in a paper, and then share it around the world, and then you realize, oh, every region of the world is disconnected, and everybody has their local units of measurement. Right? This tool here, what's it called? Ruler. Wait, why is it called a ruler?
It was made by
Boom!
And then he measured his foot, and then the servant measured with his foot, and the feet were different sizes.
Oh, yeah. People have different size feet. Maybe it's the size of the ruler's foot size, right? That's called ruler. I don't know. Read that on the internet where everything's true, so it probably is. But you go to different regions of the world and got different things, different sizes, and everybody has their own units of measurement, so it's kind of hard to share data. Metric system is one of the first systems where people got together and said, hey, let's have like a standard way to measure things, and let's also clean up all these conversions and prefixes. So, for example, in the States where we use a lot of units that came out of England, so you have to memorize a bunch of conversion factors like 5,280 feet a mile and 16 ounces of pound, yada yada. If you guys know metric system, everything's just base 10, right? Just scale everything by 10, right? So it's really nice, very logical. Okay. Where does the system come from? Where and when in time did people say, aha, we're going to create a metric system? Close. Right continent. A little bit west. Oh, okay, that was not very helpful. Yeah. Closer. How about what was going on in the 1790s in Europe? French Revolution. Yeah, you guys remember that? Everybody was having a guillotine party, chop, make some changes. So they were looking at what happened just in the United States. Said, hey, they have a republic. We want a republic, so that sounds cool. You know what? While we're changing everything and chopping a bunch of heads off, let's also revise our measuring system. We'll come up with this metric system, ways to measure things. So I'm going to throw you guys some units. Let me start with this displacement or distance. Now the base unit for that is meter, 1 meter, and the unit is just M, but you have to be careful about M because M can mean many different things in different contexts. Yeah, as a unit, it means meter. As a variable, it means mass. And as a prefix, it means milli. So be careful about that one. You guys know what 1 meter is. It's about 3.28 feet, somewhere about there. This thing right here. Where does this come from? Like, why is this distance? Why did a bunch of people get together and say, aha, this makes sense as a base unit of distance? Like, what is this based on? Nobody's foot size. Like, oh, what is this? I'll tell you the original definition. The original definition was, look at the Earth. Here's the whole Earth. A lot of the properties of the metric system were based on either properties of Earth or water. Right? You go from the North Pole down to the equator, and you split that into 1/10,000,000th. You get one of these right here. Right? That was the original definition of a meter. Interesting history, real fast. For a long time, the base units, including, were based on physical objects. So there was like, some physical rods that were stored in Paris for a long time. Scientists have tried to get away from physical objects. There's some problems with physical objects. Temperature changes, the materials expand a little bit, and then all the definitions are off. So nowadays, physicists have been able to base all these on physical constants. Go ahead, Warren.
If the meter wasn't made yet, how did they what measurement system did they use to measure how long the meter?
Well, you can use it. You can use other types of measurement systems, whatever was around at the time. Like the French had inches, the English had inches, which is two different kinds of inches, right? And then you can say, well, we know what this is. Well, now we're just going to establish this as a new system. They have ways of measuring things. Does everybody have a regional difference? Right? Yes, that's a great question. That's a good thing to think about. Like, very, very good meta type question. How do you measure? It's not something to measure, right? So, talking about here, right? And you can know the size of the Earth if you say poke sticks in the ground many kilometers away from each other, and then it's like you compare the shadow sizes and know the sun is a long way away. People figure out the size of the Earth very accurately within about 2%. Thousands of years ago, people know the size of the Earth. So trying to meet the physical constants for the definitions. So the modern definition of a meter is like the distance that light travels, because speed of light is a constant, right? Nobody knows why it is what it is, but it's something. Right? In some very brief interval of time. Let's go on to mass. Mass. The base unit is the kilogram kg. Okay. Now this is the only base unit of measurement that has the prefix baked into it. See, K is kilo, it's a factor of 1,000. That's 1,000 grams. This one threw me for a loop the first time I was learning it because I took this class called chemistry and we just worked in grams all the time, like little amounts of stuff. It is kilogram, and that's going to be important because when we start combining these units to make composite units, this will be like an ingredient that's baked into the cake, right? So it's just the kilogram, okay? This guy right here, this is the base unit, okay? The original definition was if you go 10 centimeters by 10 centimeters by 10 centimeters, make a box and fill it with water. That was the original definition of a kilogram. Time is second. S. You guys know what 1 second is. Take 1 Earth rotation, divide by 24, divide by 60, divide by 60. Okay. Quick side note, historical. There was a period of a few years where some metric units were attempted for seconds. If you take a day, divide it into 10 hours, divide that into 100, divide that into 100. Actually, it landed pretty close to our modern day seconds. That convention did not stick around. Okay. Now, these three right here is what we care about the most. You can combine these three base units and make all different kinds of units. For example, force. Does this have a weight that's pulling down right now? Right? The unit of weight is the Newton. You guys know that. Remember pulling the donkey at the start of class today? So many newtons of force. 1 Newton, what is that? That's 1 kilogram times meter per second squared. Okay. That'll make sense in a few weeks, but it's a composite unit. And there's a bunch of other composite units. There's some other ones down here real fast. You guys know, actually, I want to do this one next. Electric current, we'll touch on real fast, probably in February. That's the ampere. You got temperature. You got Kelvin, capital K. We got just counting stuff is the mole. That's that crazy big number, 10 to the 23, whatever. Hey, it's a chemistry thing, don't worry about that too much. And then luminous intensity. Like, how bright is something? Candela, CD. Now this one we won't really touch on either, but say you see a star at night, like that's a really bright star. Is that star always that bright, or is it like blowing up or something? Maybe this could be a way you could quantify that. But these three here is gonna pretty much get us through the class. Just this top three, we'll rearrange it, create all kinds of composite units. I also want to talk about prefixes with you guys. Remember metric system, scale-based 10. Now, I'm going to run out of time if I don't do it this way. You guys remember this page I gave to you on the very first day class? Everybody's got this? Also in Google Classroom? Down at the bottom, on the back, it says common prefixes. We got giga, 10 to the 9, that's a billion. Mega, 10 to the 6, a million. Kilo, 10 to the 3rd, that's 1,000. Milli, 1,000. Micro, 1 million. Nano, 1 billion. Know those are, well, they're going to know. They're going to come up in this class, okay? So you guys got prefixes? All right, so we're doing pretty good. Tomorrow I'll do scientific notation, dimensional analysis with you guys, maybe a little bit more vector practice. Get you guys ready for Friday. Yeah, Paul?